And it turns out, I was telling everyone, it's looking like Zoom did some kind of upgrade. And when I'm recording, it actually only records me now. So you don't have to turn your videos off, it seems like. All right. The key to doing 12 and 13 is you have to figure out what kind of bonds you have. And it can be helpful to redraw the picture. This is saying the carbon has a double bond, and then H is plus H2O, which I'm pretty sure you all know how to draw. You don't have to show the dots, but you can. And then this would be that this carbon has 3 hydrogens. This carbon has 2 hydrogens. And then there's an oxygen, and then there's a hydrogen. So Kobe, that's kind of back to the question you were asking me earlier. Now in 221, when I would write a compound, like when I would write a formula like this, and in 151, you guys would all go crazy. You're like, why are you writing the formula like that? And I would smile and say, well, when we get to 222, you'll see why. And so it's just saying how things are attached. So what we have, we're going to do bonds broken. So state the formula, guys remember that, minus bonds formed. So it is the direction of the equation. It is what you start with minus what you end with. So we have carbon, we have 4 carbon hydrogen bonds, a carbon-carbon bond, and 2 oxygen hydrogen bonds. And so that's going to be our bonds that are broken. And then over here, we have 5 carbon hydrogen bonds, a carbon-carbon bond, a carbon-oxygen bond, and an oxygen-hydrogen bond. So this is the key, is making that list of all the types of bonds. So you have the carbon-hydrogen, then in the middle we have a carbon-carbon, carbon-oxygen, oxygen-hydrogen. Now, before we go on and write all the numbers, you can actually reduce. So these 4 carbon-hydrogen bonds, technically, I don't like that color, it's not showing up. These 4 actually will reduce this. So we only actually end up with 1 new carbon-hydrogen bond. And then this oxygen-hydrogen bond is actually one of these. So technically we can reduce that just down to 1. And then you need that chart. And you just look up your numbers. So the carbon double bond is 610 kilojoules. And the oxygen hydrogen bond is 463 kilojoules. So Araceli, this was the, oh, you were working on the second one. I can't remember now which one, but that's the idea. And it can help to make a sketch to figure out your bonds. And then when you look up the carbon hydrogen, you should get 413. The units are actually kilojoules per mole, or you can just say kilojoules. Carbon-carbon is 346 and 358 kilojoules. Make sure you use parentheses, right? So bonds broken minus bonds formed, and you should get negative 44 kilojoules. All right, for number, so there is one on your worksheet. Combustion, remember, means plus oxygen, and you're going to make CO2 and H2O. And then there's a bonus question that takes you back to last term. So the bonus question, you actually will do products minus reactants. So it's the opposite way. It's a little funky, but it's a couple people have already done it and they got the answer good. So CH4 just means we have a carbon with 4 hydrogens, but there's going to be 2 of them. So we actually have 8 carbon hydrogen bonds. So there's 4 times 2. Oxygen, O2, is always a double bond. That's the only way it works out. And if you want, again, it's up to you if you want to show dots. So we have just 1 oxygen double bond. So those are our bonds broken. And then minus our bonds formed. And so, Again, this we will double. So CH3 and then an OH. So that's what it's saying is you have three hydrogens on the carbon and then an OH. Carbon likes to make 4 bonds. Carbon always makes 4 bonds. The only exception to that I know of is carbon monoxide, and is probably why carbon monoxide bonds to hemoglobin so much better than carbon dioxide. All right, so what we have here are 6 carbon hydrogen bonds. So there's 3, and then we double everything. We have a carbon oxygen bond, but we have to double it. So we have 2 carbon oxygen bonds. And then we have the oxygen hydrogen bond, but again, we have to double it. So everything on this side, what you get, you have to double. And then we can actually reduce. So it is the carbon hydrogen bonds. We can actually cut those down. So over here, we can reduce that to just 2 of them. And then we would have 2. Now, the comment I will make to you, that this was probably my biggest issue in the past every year for 25 years, is labeling. And if you look when I do it, if you're writing the number directly under the type of bond, I'm okay with you doing it like that. If you're just writing numbers all over the place and I can't figure out what kind of bond you're talking about, you're not going to get full credit because it's not labeled clearly. So as long as you line them up, you can also make it as a list and then just write it next to it. All right, the 2 times the 413 kilojoules plus this one's 498 because it's a double bond, so it's going to be a high number. So those are our bonds broken. And then over here, we're going to have 2 358. Now these are single bond carbon oxygen. When you do the one on the worksheet, it is a carbon double bonded oxygen, so you have to be careful. And then 2 oxygen hydrogens. You don't have to reduce, it's just going to have a lot more numbers that you're adding up. And then these are, so you add these and then you subtract all of these and you'll get my number. In both cases, they're negative. So questions with that? And that's the second page of the worksheet, has you write an equation and then you just use that chart and then just show the bonds broken, just make your list and then reduce. I like to write all of them and then reduce them. All right, so drawing. So
Sorry,
NO3, go ahead.
Oh, not a question. Just let me know if you want me to turn off my camera, just because it's too much moving by me.
I don't see you.
Okay.
You came in late today, so you got like demoted from the top of the class, Major. And it turns out it doesn't videotape any of you guys. I don't know if I save it in a different way, but it only shows me. So too bad. You can be the host if you guys want to be on here. So 24 electrons, the only way this will work out is you need 1 double bond and the others are singles. It doesn't matter where you show the double bond because this is a resonance. I didn't ask you to say that, but it is nice to recognize. And so this was a question a couple people asked me because on the lab 1 that you turned in, there were only 2 resonances on the whole lab. A resonance means you have to have a double and a single. And they have to be between the same type of atoms, so between nitrogen and oxygen in this case. All right, formal charges are the group number minus, this is how I do it, lines plus dots. It says lines. My brain, I honestly have trouble with the idea of formal charges, and so I have to simplify this. So nitrogen, its group number is 5. And so it'll be its valence. Group number means its valence electrons. And then it has 4 lines. So it'd be 5 minus 4. So it's going to be a +1. This oxygen with the double bond, it's going to be 6 minus 6. So each line you only count once, and each dot you only count once. Again, this is me simplifying the actual definition of formal charges. You get the same answer. So this is a 0. This is going to be 6 minus 7. So 6 dots in one line, so -1. And this would be 6 minus 7. So that's doing formal charges, except my answers are not right. So this was the question that shows up on the worksheet also. So pay attention so you get right on the worksheet. Because it's a resonance, we're going to average all the oxygens. So all the oxygens are actually a formal charge of -2/3. So none of them are 0, none of them are -1. You add all 3 formal charges, not the nitrogen, just the oxygens, and you add the 3 up and divide by 3, so -2/3. So that's the idea of a resonance, that they're all equal. All right. On B, there's only one answer, and then there's several ways you can explain it. The hydrogen attaches to the oxygen. So according to formal charges, it's because the oxygen has negative, and that's going to attract the hydrogen. That would be the technical definition. Another way that I will have about half of my students explain it, because this makes more sense to them, the nitrogen already has a full octet. It has 4 bonds. Nitrogen cannot break the octet rule. So there's no room for hydrogen there. If we draw, I think I asked you to draw the Lewis structure, yeah. Once you attach, the hydrogen is going to attach to one of the oxygens that has a single bond. Once you do that, this oxygen is actually no longer part of the resonance. So I didn't ask you to do formal charges, but I'm going to do them again. The nitrogen's still +1. This oxygen now would be 0. This oxygen would be 0, and this one would be a -1. However, you would only average these two. Yeah. The sum of the formal charges must equal the charge of the compound. So this, once we add the hydrogen, if you add up all our formal charges, you end up with a 0, and we have no charge anymore on nitric acid. If you add up all our formal charges up here, we do get a -1 because our compound had a -1. The negative for the formal charge, you do want on the more electronegative, which is the oxygen. Any questions? So you'll see a formal charge question on your worksheet, and you'll see one on your midterm. And some people are obsessed with formal charges. My son's teacher was. If you go online, there are many websites, and they think that you can solve everything with formal charges. I am not somebody who buys into that, and I think it's because my background's biochemistry. All right, so more drawings. So for hydrazine, this is saying we have a nitrogen with 2 hydrogens, and then we're going to have another nitrogen with 2 hydrogens. So sometimes we like to write compounds. It's trying to show you how it is. Hydrazine, by the way, is rocket fuel. So if you, you guys are picking a molecule sometime in the next week. So like somebody sent me a citrulline. It's like the angel wand. So I know Kobe's going to end up picking some kind of rock to do his on. You can do an explosive. You can do a neurotransmitter or a hormone. Oxytocin is the molecule of love. So you can pick like the molecule of love, or you can pick like cadaverine, which is the smell of death. So that's the molecule that dead bodies give off. So you can pick like what kind of talk you want to give. That might appeal to some people for some reason. All right, if we count our electrons, nitrogens have 5, so that's 10 plus 4, so 14. And so right now we have 2, 4, 6, 8, 10, so 12, 14. So the nitrogens just get dots. Remember, no dots on hydrogens. You cannot double bond to a hydrogen. For the N2O, we get 16 electrons. And we did this one last week. The triple bond actually goes to the nitrogens because the oxygen's so greedy. And so if it's the same element on each side, then you would do a double-double. But if they're different elements, one of them will keep the single bond. So the shorter one is the triple bond. When we and the stronger one is also the triple bond. We're going to be looking at this quality tonight. We look at valence bond theory, and then even more on Thursday. All right, and then the bond angles. So our first one, this is 109 degrees. I also wanted to mention, so I go with, this is a tetrahedral pyramid, right? So nitrogen has, you have to get in the habit where you like block half of it and you're looking, you don't want to cover up the bond, but the nitrogen has 3 single bonds and a lone pair. So this is a triangle pyramid or a tetrahedral pyramid. You can also look online and they'll give you funky numbers, but some of the numbers online are actually a little bit too funky. So please be careful if you decide to use Google to look up everything, because I just know this, there's a lot of really bad information out there about this. So I recommend just going with the 109, and this is of course linear. So this is 180 degrees or linear. On the lab, some of you, most of you, I wrote comments to, and so please ask tonight during office hours or something if you have questions, because we do have, your celebration is next Thursday, and it is all drawing and doing these, and so in this environment, usually I have really high grades with this because I get more interaction, and in this Zoom environment, that's a little bit constrained. But last year they did pretty. Last year we had problems with cheating on this exam, so we're not going to go there. Maybe that's why I'm smiling so much, because I'm like, you guys are not going to do that to me. We had a lot of problems with cheating last year. All right. Bond angles for 1, 2, and 3. So this is just practice. So the lab this week, I just posted it right before class. It is organic chemistry. It's all organic chemistry. It is, you sit and listen to a video, you follow along with me. I posted the video. I had to split the video into 2, and I go through filling out these 6 pages. And I have molecules that I like have in the screen as I'm doing it. This was like the first time I got to use this overhead, was to do this lab. And then, yeah, and then the post lab is just like the last 2 or 3 pages, whatever it says on there. So you actually have to watch the video, but it does a lot with carbons, and it will help you. It makes a difference that by next Tuesday when you come in, you should look at these pictures. Even by this Thursday, the study set for Thursday is a lot of these where we look at these pictures and you tell me bond angles. We're going to add a dimension to it today. All right, so bond angle, so 1 is 120 degrees. That this carbon, again, you can do something where you cover part of it up, but that carbon has 3 things around it. 109, the tetrahedral, is only going to happen if the carbon has 4 single bonds. So that doesn't happen. This number 2 is 180 degrees, and then this number 3 is 120 degrees. The shorter bond is the double bond, so the carbon double bond, and also the stronger one is the carbon-carbon double bond. When you're comparing, it's specifically saying the carbon-carbon bond, because when you start bonding to another element, like the nitrogen, the size of the atoms does change the size of the bonds. We're down like looking at picometers and nanometer sizes. And so this is all theoretical numbers. All right, so the electrostatic potential, my printer didn't print in color, but the nitrogen is negative, right? It's the most electronegative. So that's what it was trying to say, or you could draw it here as negative. So it's pulling. The pull is towards the nitrogen, which would be this way, towards the nitrogen. We'd show the positive on the end with the carbons and hydrogens, or you can do it on this picture that it's pulling. So electrostatic is, right, positive, negative, and that's what this is all about. The delta is for dipole. It just means a partial pull of the positive, negative. The most polar, the only polar bond is the carbon-nitrogen triple bond. And is the molecule polar? We're going to talk about this more tonight. This one is, yes, because of that nitrogen. We're going to go more in depth with this tonight and on the next study set and worksheet, because there is a limit. Once the carbon part gets too big, it becomes not polar. And the general rule is like 6 carbons. It's like a hand waving rule, but this is still pretty small. So the nitrogen will pull it into the water. All right. Cyanate is actually a stable-ish ion, a close relative to cyanide. And then there is fulminate, which is this. And that is telling you the nitrogen is in the middle. So you can do where you put a double-double. This is going to have 16 electrons. So you can have a double bond to the oxygen and carbon. You can do, if you want, you can show your negative. You can do a triple bond to the carbon and a single bond to the oxygen. You're like, yeah, that makes more sense because nitrogen, try it one more time. Oxygen, right, is greedy. It wants a single bond. None of these make any sense. Or you can put the triple bond. Why not? So the whole idea with these, what we draw on paper, we can draw anything on paper. It doesn't mean it's going to happen. When you guys are asked to draw Lewis structures, like on your worksheet, you want to make sure you draw what is the most probable structure and stuff, following the octet rule whenever possible. And then you put your dots. We need the dots to be, so that we can do the formal charges. All right, so those are our 3 pictures. It's wanting you to put the nitrogen in the center. Formal charges. Oxygen here would be 6 minus 6. So again, it's valence electrons are 6, and then subtract the dots in the line. So that would be a 0. On this one, the oxygen is going to be 6 minus 7. So -1. So you're like, oh, that sounds great. And then this one, it would be 6 minus 5. So a +1, which is like, that doesn't make sense. The nitrogen every time is 5 minus 4. So every single one of them is nitrogen is going to end up with a +1 because it's the monkey in the middle here. Now, when we add up the formal charges, we have to end up with a negative. And so that's what happens. The carbon has 4 valence electrons. You subtract the 4 dots and the 2 lines. So this is 4 minus 6, which is -2. That makes no sense at all for the negative to be on the carbon, not the oxygen. Same with this one. We get a 4 minus 5. So carbon is a -1. That's a little bit better because the oxygen also got to be a -1, but it's still, the nitrogen is more greedy. And then this one would be carbon's a 4 minus 7. So 6 dots in the line. So carbon here is a -3. This is, and the Oxygen is a +1. That one makes absolutely no sense based on formal charges, but without even doing formal charges, you should be able to say oxygen doesn't want a triple bond. Oxygen's one of the greedy ones. Like if nothing else you get from this whole term, oxygen's greedy. It does not make a triple bond. So based on formal charges, which of these is most reasonable? I would have to say it is this one. So you want the lowest formal charges possible. And it's giving the oxygen the -1, and it's the greediest one or the most electronegative. And also they're the lowest numbers. And our oxygen reason. All right, and then the last question, this guy is really unstable. It is actually used as an explosive to blast out the old stumps in the gardens. And why is it so unstable? None of them make sense. So carbon likes to be the monkey in the middle. So carbon likes the middle position. Nitrogen is greedier. It wants to be on the outside. Yeah. So however you want to phrase that. On your celebration, which is scheduled for next Thursday at this moment, we're going to do it. And next Tuesday, we'll be doing a review practice. There are a lot, it's all show your work. And so there's going to be where you have to give explanations. So just a lot of the explanations have to do with nitrogen, oxygen, fluorine. So NO and F are the 3 greediest that there are not. It's why they're special. All right, any questions from the study set? If not, I'm going to stop and then we'll move on.